Good morning. So today I'm going to give the second lecture of the first topic, and you have seen in the first lecture what I have discussed, primarily the importance of photovoltaic solar cell and some of its applications in domestic as well as in large scale applications. And then what we have discussed, that what are the materials that people have investigated in order to fabricate a solar cell. And then one of the most important material which we have seen that people have started with is silicon. Silicon is an important material because silicon was used in electronics industry for a long time. So the properties of silicon were known, although it has indirect band gap semiconductor, and generally the light absorption of silicon is less as compared to some of the other wide bandgap semiconductor which has direct bandgap, but still people have started the photovoltaic technology with silicon. And then what we have seen is that how silicon can be used as a junction, diode junction, PN junction, which is known in the semiconductor industry, and the same PN junction can be used as solar cell. And then what is the typical device structure of a solar cell? So when we analyzed a solar cell, a simple homojunction solar cell made up of silicon, what we have seen that it actually has different interfaces. So PN junction is one interface where a p-type and n-type semiconductor make a junction. Another interface is the contact layers. So the n-type is connected with one particular contact layers, which is gridded layer, mostly made of metal, and the bottom one is another metallic contact layer. So it is basically two more interfaces which are incorporated in a silicon solar cell, and therefore when light falls on a silicon solar cell, it actually produces electron and positive ions, or electron and hole you can say, and then they are migrated through the contact layers to the outer circuit. And the driving force behind that is the depletion layer, which also we have discussed. So if we have a good depletion layer, we have a good depletion of built-in potential or built-in electric field, then we have a good driving force, and then electron can move towards one of the interface and can go in the outer circuit, and which is being used as current, and then as if you drop it against a load, then you get a voltage. So this is the way the power is being generated in a homojunction silicon solar cell. And then we have discussed about some of the parameters of the solar cell which are important. So what are the parameters we have discussed? Our ideality factor, and then potential barrier, and then the shunt resistance, series resistance, etc. And then when we illuminate a solar cell, then other parameters like open circuit voltage, short circuit current or short circuit current density, and then fill factor, and finally the efficiency of the solar cell can be calculated. And you will see that in future, whenever we will discuss about solar cell, various solar cells we will discuss in this course, and you will see that most of the time we will actually look around these particular parameters, how one can play with these parameters, and finally making a very efficient solar cell or enhancing the efficiency. And the last part of my previous lecture, I mentioned that one optical layer which is extremely important, which is required in solar cell, because when light falls on a solar cell, it is a tendency that light gets reflected back, and particularly silicon is a good reflector. But the idea is that we have to absorb more and more light in the active medium, and if light gets reflected back, then this light is not being used. So what is the solution for that? What we have seen, the solution for that is to make an anti-reflection coating on top of that. There are several anti-reflection coating. Some nitrides and oxides are popular anti-reflection coating which people have used and investigated. And these anti-reflection coating are basically used to, to stop that reflection or minimize the reflection and maximize the absorption. That is, light should go inside the cell and then it should get absorbed. And then today we will start from the same point, that what are the other means of absorbing light more and more in the solar cell. So one was anti-reflection coating, which we have already discussed, and the today's lecture will start with what is known as texturing of the solar cell surface. And that actually gives another potential way to trap the light inside the solar cell and minimize the reflection. This is the first topic which we will discuss today. And the second one, we will discuss a little bit about the technology, silicon solar cell manufacturing and the technology of silicon solar cell. After addressing this manufacturing issue or the technology, we will see that what is the importance of thin film solar cell. And then we will discuss how one can trap light in the thin film solar cell. Okay, so let me start with my first topic, that is, or first subtopic you can say, that is light trapping by texturing. So you can see that when light falls here and then it gets refracted here, it goes inside the medium, and then again there is another part which gets reflected in this path, and then finally it is reflected and some light is trapped. So what we have essentially done here, we have made a structure. So what is the importance of this structure? And when we make this structure, this is called texturing of the surface. So the question is, what is the importance of this texturing? Now, try to understand that what is our aim? Our aim is to absorb more and more light inside the solar cell. Ideally, whatever light is falling on the solar cell should be absorbed, to make it is an ideal device. Whether practically it is not possible, as we have seen. But what we can try to absorb more and more light, more and more photons inside the solar cell. That means we have to trap more and more light. So one way is, suppose I start with a thin silicon wafer. Okay, say 1 micrometer silicon wafer. Okay, then light falls on this wafer. All right, and then there's some part of the light will be reflected, some part of the light will be absorbed, will be absorbed by the wafer, and some part will be transmitted too. Now, if I increase this thickness from say 1 micrometer to 10 micrometer to 100 micrometer to 500 micrometer, then you will see the component of absorption will increase. You can say that, okay, what we need to do, we just increase the absorber thickness. That means the silicon wafer thickness, make it say 1000 micrometer silicon, then entire light will be absorbed. That is what we require. But there are some issues. You cannot make a wafer as thick as possible as you want as far as the absorption is concerned. Why this is not technically possible? The reason is one, more and more thickness you introduce of the wafer, more and more cost is involved. Okay, you increase the cost of the device. This is one issue. Second issue is more and more thickness you introduce in your wafer, higher and higher recombination takes place. Although you absorb more light by increasing thickness, but recombination is more inside the thick cell or thick wafer. So we have discussed about recombination also in the last lecture. If you remember, we have discussed a band-to-band transition, we have discussed a Shockley-Ridall, we have also discussed Auger recombination. Okay, so if the recombination increases, then eventually, you know, the charge carriers which should flow outside the circuit is reduced, and therefore you do not get a voltage which you are looking for. Even if you have a thinner cell and you have less absorption, you can produce more voltage in the outer circuit than the voltage for a thick cell where you have more absorption because of this issue. So there are two important factors that we cannot keep on increasing the thickness of the wafer and make a solar cell, and therefore what is required, as I have shown you, that you make a kind of texturing on the surface. So that is what is known as texturing. You can see that it is a triangular surface. Look at here in this. So here it is, you know, what you do, you have silicon. Silicon is a crystal, it's a cubic symmetry crystal, and then you etch it, chemically etch it along certain phase. Okay, so I'm not going to discuss with you about the chemical etching process, but you may be knowing this is a very fundamental process. One can chemically etch towards a particular direction or particular phase, and one can make a pyramid kind of structure. Here you can see pyramid kind of structure on the surface. That is what you can make. Okay, and people have done it. And you can see a real image of this pyramid kind of structure here. Okay, this is the scanning electron microscopy image of the pyramids of the surface of silicon. So if you have a pyramid, you can have a better light trapping, as you can see here in this particular, the illustration. Okay, so let me come back with different steps of light trapping. Okay, let me start with a situation. Say you have a solar cell, okay, and light is falling on this, and this is your front surface, and this is the rear surface or the back surface. Light falls in this structure. So you have two layers now, front and the back, and light falls in this manner. It gets reflected back here. So this is a typical optical path. So if you have a back reflector, back surface or a back reflector, you can reflect light back. If you do not have back reflector, then the light will be transmitted. Okay, so if you have a back reflector, what happens? This back reflector also reflects light back. So what essentially you have done is, you can see here it is one optical path length. Okay, if you do not use this back reflector, then this light goes out, then you have only one optical path length for that particular ray. Okay, and now you have another optical path ray, one more. So by introducing a back reflector, you can see you have 1 plus 1, 2 optical path length. This is important. This is what you essentially did when you were increasing the thickness of the wafer layer, increasing the optical path length. If I have 1 micrometer wafer, I have a little less optical path length. If I have 10 micrometer wafer, I have higher optical path length. If I have 100 micrometer wafer, we have more optical path length. But now I have not done it. I did not change the wafer thickness at all. I just use a back reflector here and make the optical path length twice, double. Okay, so this is the first step which we can do. Okay, now what I can do, I can make this front surface, this earlier it was a flat surface, now I have a textured surface. I make a textured surface. Okay, so now light gets reflected here. Because of textured surface, light gets some angle. We know this angle of refraction and angle of reflection. If you remember that Snell's law that tells you about the angle of refraction, n1 sine theta 1, to remember this law, right? This is Snell's law. What is n1? N1 is the refractive index of the medium from where light is falling. N2 is the refractive index of the medium where light is going inside. And theta 1 is the incident angle and theta 2 is the angle of refraction. Okay, as light is refracted. So now this angle of refraction is changed because now there is the surface is not the plane one. The silicon surface or the top surface is now textured, sort of triangular shape. So you have reflected light here and then it comes out. Now you can see your optical path length has enhanced. Okay, earlier it was like this and now you have a slightly enhanced path length just by texturing the top surface of the wafer or the material, whatever is there on the top. You have enhanced the optical path length. So optical path length increases. But you know, this is making this surface texturing is a technology. Okay, it is not very easy. As I mentioned, that one is to very controlled manner. One is to etch the surface, chemically etch the surface along certain phase of the material. Now I will do the third one. So now you can see the top surface is textured and the bottom one also is textured. Okay. So now what happened? I make both the surface textured. So bottom one also I make a sort of structure inside, and then what happens? Light falls here, it will be reflected here, then it will go here, and then again it will be reflected, go here, and reflected back here, reflected back here, and then after multiple reflection, why multiple reflection takes place? You remember there is one thing which was known as total internal reflection, which you might have studied in school. Total internal reflection is a reflection if the incident angle is more than certain critical angle, when the refractive index of the top layer or the top medium is higher than the refractive index of the bottom medium, then the light after certain critical angle gets reflected back to the surface itself. Okay, and that is called total internal reflection. So by using the total internal reflection, what you have done, you have now enhanced optical path length multiple times. That is what actually we are looking for. So this is basically a technology, texturing. Okay, so you do not increase the thickness of the layer, do not introduce more recombination, but you increase the absorption capability of the material by increasing its effective optical path length by making the surface texturing and also the texturing of the bottom layer or the reflector. So this is what people have done, and they have introduced in their solar cell this particular texturing, and now you can see this particular figure. The red line is the blue line. First you see, this is when there is no light trapping. Okay, and there they have measured the short circuit current density when there is no trapping of light. Okay, or the surface is were not textured, and then the red line is the short circuit current when the surface were textured or in a textured solar cell. So there is a quite large enhancement of the current, because if you take now a thin solar cell of say 1 micrometer, for this one you have around 10 to 12 milliampere per centimeter square short circuit current density, whereas for 1 micrometer thick you have 35 or above the short circuit current density milliampere per centimeter square. This is amazing. Okay, even you can say when we use say 100 micrometer solar cell, which is typically a thickness, there of course for 100 micrometer solar cell you increase the short circuit current density. So this becomes around 35 milliampere per centimeter square, which was possible in case of textured one just for 1 micrometer solar cell. Okay, and now you have 100 micrometer solar cell, and without texturing your current is around 35 milliampere per centimeter square, and the current for the textured one is definitely high. It is almost about 42 to 43 milliampere per centimeter square. So the issue which I discussed is very clearly shown or demonstrated in this particular experiment done by this in the research work. Okay, so you have to appreciate that it is not only the enhancement of the thickness which will increase the short circuit current density, but also it is the texturing which is even more important. Then I can go for a very thin wafer and I have almost similar current density. Now we come to technological aspect, silicon solar cell manufacturing. It is important to know about this. It is always important that whenever we know certain basic information or the fundamental information about a particular material or a particular device, it is also important to know subsequently how this is practically people make. So therefore a little bit discussing about the manufacturing technology is important. So how solar cell is being manufactured? What is the raw material that you start with for a solar cell? Raw material is nothing but sand. Okay, it is SiO2, silicon dioxide, or when you look for a very highly refined kind of raw material, you can also think a very good quartz crystal that can be used. However, a raw material is simply use sand, that is SiO2. You start with begin with this raw material. So how do you produce this? The metallurgical grade grade silicon, that you do some kind of carbonization, and then you produce metallurgical grade silicon, and carbon dioxide is produced in this uh, reaction. Okay. So what is metallurgical grade silicon? Metallurgical grade silicon is basically being produced a large quantity every day, and these are being used in many purposes, metallurgical grade silicon, and not for very sophisticated uses like solar cell. You need little more refinement of the silicon to introduce it in the solar cell. Okay, but if we look at the different components or different impurities they are present in metallurgical grade silicon, one can look at in parts per million the concentration. So you can say there are many elements starting from aluminum, boron, calcium, chromium, copper, iron, magnesium, manganese, molybdenum, nickel, phosphorus, titanium, vanadium, zirconium, etc. There are many elements present in this metallurgical grade silicon, although metallurgical grade silicon is also a pure silicon, you can say, but the purity level may be 97 to 98%. So there are many elements which are present as impurity in a metallurgical grade silicon and cannot be used for a solar cell purpose. But let me tell you that whenever we produce this metallurgical grade silicon from sand, what is required is very high temperature process, almost 1400 to 1500 degree centigrade, high temperature process. So you need very high temperature furnace for this process, and therefore it is costly. I will show you few real chamber where people do produce this silicon. But this is the reason why you have a very costly equipment and costly process. But one cannot help because one is to start with making a metallurgical grade silicon by high temperature. But now what you need to make an electronic grade silicon, and that is what is required for your integrated circuit or the electronics or in the semiconductor solar cell or many other semiconductor devices. Then you need some more process. You have to treat it with HCl, hydrogen chloride, and you produce SiHCl3, and then hydrogen is produced, and then you put it again in a reduced environment in hydrogen. Okay, so that here you do not need that a high temperature, but you need high temperature up to 400 to 500 degrees centigrade, and it should be in a vacuum environment so that your impurity level is reduced. And some of the component they also make their halide and they get segregated. Okay, so the finally what you produce is the silicon of electronic grade. Okay, and this is very pure silicon. Okay, so what are the types of silicon one work with? With when we use it for solar cell particularly, or for any other industrial purpose. But for solar cell, these are the silicon. So you can make a differentiation of the silicon. So it starts with single crystal silicon. Okay, single crystal silicon is highly pure single crystal silicon, but with a large grain size, and you have to use some special crystallization technique like Chorovsky or CZ technique or float zone technique. So I am not discussing here the crystal growth technique, but crystal growth technique is an integral part of the manufacturing process of silicon. So I would suggest that one should go through this crystal growth technique also, CZ technique or FZ technique, to understand it better. Okay, these are very standard crystal growth technique which are being used for making a single crystal silicon. Okay, Or one can have multicrystalline silicon or MC silicon with little less grain size. Okay, this can be common techniques which are used by casting, or one can make a ribbon type of multicrystalline silicon. One can have polycrystalline silicon also, where the grain size is less, and then here you can also use a chemical technique like chemical vapor deposition, etc., to make a polycrystalline silicon, and these are also used for solar cell. Or one can have microcrystalline silicon whose grain size is even less, and one can have a physical technique or a combination of physical and chemical technique like plasma deposition, etc., to grow a microcrystalline silicon. So generally, when we use the silicon as a material, we use single crystal silicon or multicrystalline silicon for solar cell. But this is a broad classification of the different silicon crystal which one should know before one make the silicon solar cell. Okay. So let me go little more basic. So when you talk about single crystalline silicon, this is the typical, the atomic structure you see in case of single crystal silicon. As I mentioned, that it is in a cubic symmetry, this silicon as a material. But if you look at atomic level, that one is silicon atom is basically coordinated with 1, 1, 2, 3, 4. 4 silicon atom with 4 bonds. It is 4 valence electron, so you can make a very nice bond with 4 nearby silicon atom. Okay. But these silicon as the atomic structure of the single crystal silicon, as we see here, is not capable enough for a silicon solar cell, although it is pure. Why? Because it doesn't have charge carrier. It doesn't have free charge carrier. They are all bonded. So in order to make free charge carrier, you have to either dope N or P. Make it N or P. Okay. So you have to introduce N-type or P-type, and these are typical dopant which are being used. N-type is basically group 5 element like phosphorus. P-type is basically group 3 element like boron. Okay. And we know this is very basic and fundamental thing. Whenever you introduce an N-type, you have an extra electron on the surface, making it N-type. A large number of free electron density you get in case of N-type silicon. And similarly, when you dope it with boron, then you have a hole generated and large number of holes. So now the question is, in this case, electron is the majority carrier, and here holes are the majority. Okay, and in this case hole is the minority carrier, and in the second case the electron is the minority carrier. Okay, so this is a very basic thing of a single crystal silicon. So this is being used when you make an N-type and P-type, and then we have already discussed you fuse one N-type with P-type, make a p-n junction, exactly what you did in when you make a diode, and then we know how one can make a solar cell. Okay, so what about multicrystalline silicon? In case of multicrystalline silicon, you can look at, now I have different orientation, multicrystalline. So they are actually they are pure, highly pure crystalline silicon crystal wafers only, but they are multicrystalline. That means the grains are crystalline grains are oriented in different directions as shown here. So it produces something when you have two grains, like this is aligned in this way, this is aligned in this way, this is aligned in this way, this is aligned in this way. They produces something called grain boundary. You can see this is a grain boundary, and grain boundary is a defect. Okay. In single crystal silicon, look, In the atomic structure, we did not see any grain boundary. But now we have the grain boundaries by making multicrystalline silicon. And when grain boundaries are introduced, they act as a defect, and they also, these defect act as a recombination center. Okay, so for multicrystalline silicon, you expect the efficiency of the silicon solar cell will be less, because if you have more recombination, it will actually reduce the charge carrier whatever being produced, and therefore multicrystalline silicons have little less efficiency as compared to single crystalline silicon. However, for single crystalline silicon, you need very refined method to produce. So these are the balances. So these are the typical, the technique which in technology people use. So these are when one make a huge silicon polycrystalline ingot, you can see it starts from this. When you start processing from sand to in your journey to a silicon wafer. You start with a huge, large size of ingot, and then you make a bricks of silicon, say multicrystalline silicon, and then in the third stage you have to cut them, slice them into wafer. Okay, so this is actually a production line which one follows when one make, starting from sand to the wafer, silicon wafer. I will discuss it a little more here. So let us now look at this journey. So as I mentioned that you have to start from, say, sand, and then you have to go to a module. Okay. So what are the steps involved? So first it starts with sand, as I mentioned, and then what you require is purification of the sand. The first step is purification. Okay. And second is you need it to reduce with carbon. Okay. And then you put a metallurgical grade silicon. That is what I have already discussed. That is, this SiO2 reacts with carbon, and then it produces metallurgical grade silicon with carbon dioxide. This is the second step. And third step is crystallization. Okay. And then wafer production. So I mentioned that there are different crystallization technique like CZ technique or FZ technique. Okay. So once you do this crystallization and make a proper crystal, and then you slice them, all right, and make a wafer. And then this wafer is used to make a silicon solar cell device. Of course, before you make a device, you have to have the doping process. Okay, after wafer you have doping, and then silicon solar cell device. So doping I have already discussed. You have to dope it with either n-type impurity or with p-type impurity and make a junction and make a solar cell device. And then you connect different solar cell device in a module and make a complete panel of solar cell. That is what we see as a solar cell panel. Okay. So let me just make a small block diagram here. Okay. So I start with sand. and then I do purification, followed by I add carbon, I use metallurgical grade silicon. Okay, so this is a step, and then I treat it with HCl. That is what I have already discussed, and this you produce halide. Okay, do a sort of distillation. This is the next step. Okay, so as I already mentioned, that metallurgical grade silicon are not pure. There are different impurities, and therefore you have to add the HCl and then do distillation and then add hydrogen and then make silicon of semiconductor grade or electronic grade. Okay, so these silicon are now they have to, we are using the wire mesh or the diamond cutter. You have to make wafer. Okay, so this is the entire journey, and then this wafer is being used. So sometimes you cannot just directly use the wafer. You have to introduce a technique called lithography and make a module, silicon solar cell. So just notice that what are the entire, the process involved in silicon solar cell manufacturing. It is not a simple thing. You cannot just go to lab and deposit your silicon or grow your silicon and make a silicon solar cell. That is not possible. So when you introduce so many pathways for production, okay, from sand to here, you have to understand that every production takes, lot of the cost of every production line is very high. Okay, and also it's a very high temperature process, as I told you that at this stage it is almost 1400 degrees centigrade to 1500 degrees centigrade process. It's a huge temperature process, so you need very big and high vacuum furnaces for that. Okay, so therefore the technology, although it is very mature and people could make these steps from sand to finally to a module, and we all use this silicon solar cell. We see here and there, and if you go across the institute, you will find different buildings where there are solar cell modules. But you have to appreciate that this is being produced by through all these processes, and therefore the cost is a very important factor. And as I mentioned to you, see, there's some typical chamber where they are being produced, a huge chamber, and the kind of ingot which they make, or the kind of bricks they are made, and then the cutting process and then wafering. It is a big technology involved in this entire manufacturing process. Okay, so what are the advantages and what are the, okay, let me just, before finishing that, let me just finalize this with this, that once you have the silicon crystals, okay, then this is our known one particular device, silicon solar cell device, and this silicon solar cell device is, again, this is the active medium, that is actually the NP junction, and then you have the front contact, you have anti-reflection coating, you have rear contact, and then if you, as I have discussed before, if you make texturing on the front or the texturing on the rear, you can really make an efficient solar cell, and then finally you make a module. Okay, so the technology is complete, but yeah, definitely we should again summarize it with saying what are the production line involved. So whenever you have a technology, one has to see that production line. Okay, and the production line, you have 4 production line. It starts with silicon purification line. In silicon purification line, your basic material is sand, and the output material, this is the input material, output material is high purity silicon. This is the first production line which you use in silicon manufacturing, and second is silicon wafer line, where you use high purity silicon as input and you get silicon wafers as output. Okay. And now in the third production line, that is called silicon cell line, where you use silicon wafers as input and you get fully processed silicon solar cell as the output. And the fourth production line is use fully processed silicon solar cell as input. This is also known as silicon module line, and this is the final production line where this is input now, and finally you have fully assembled solar panel as output, which you use. Okay, which are being used for whether it is domestic purpose or for large scale application, like you make a big solar power generating station, which many people are making, and this is one of the emphasis which has been given in different countries and including our country. So therefore this entire process involved here. And if you just look at Honda has shown this particular car, they call it highly efficient car, solar car. And remember, you can see the solar panel in this car, but the kind of efficiency which it had is only 20% efficiency, but it is still highly efficient solar cell car. So efficiency is definitely an issue, and we have to address in our entire lecture these efficiency issues when we discuss different solar cell and different aspects of this. Okay, so what are the advantages? Let me again tell you that advantage is that you have a good technological background. You know exactly how to make a silicon solar cell. You have very clear production line starting from sand to panel. Okay, so entire processing technology is known. So therefore this is a most important advantage of silicon solar cell. What are the disadvantages? Disadvantages are that you have, because of many production line, you have seen 4 production line, and I also made a flow chart of the entire production starting from sand to panel, and you have seen so many the techniques are involved. Okay, and therefore it's very costly. Okay, although the utility is very high, cost also depends on how much the usage of the users. Okay, but the production cost and utility is somehow it not properly balanced. Okay, and therefore it is still being considered as a costly solar cell technology, although it is highly efficient. This is important. Silicon solar cells are efficient, as I have shown you that high efficiency car also people have made using this. But still, people have to look for alternative. Why? Because there are several disadvantages. What are the disadvantages? Because if the disadvantage is in the fundamental level. Because I did not mention it to you before. Let me just show you. It's a very fundamental, okay, when you have conduction band of a material and valence band of a material, when their K points are exactly matching, this is just one top of the other, we call it direct band gap. But if their K points do not match, this is valence band. Okay, so this is conduction band minima, CBM, and this is valence band maxima. They don't match, we call it indirect band gap. Okay, so indirect band gap is the disadvantage of silicon. Silicon is a typical indirect band gap. Indirect band gap. So the absorption is less, and therefore you have to make a thick silicon wafer. And typically, if you look at, if you just go to lab and see the students do work on the silicon solar cell, you will see that the thickness of the silicon wafer is few hundred micrometer. Okay, and then you have so many production line involved, it becomes a very costly, device. Okay, so the question is, if you do not have this 100 or 200 micrometer thick silicon, then you do not have enough absorption. Although by texturing you make a little bit, the absorption or reflection you minimize and make absorption more. But more and more the material processing you do, remember that more and more material processing you do by making texturing and the front surface or in the back surface, more and more defects you introduced in the system. Okay, more and more interfaces you generate, and therefore you have more and more recombination process also. Okay, so therefore technology has to change. That is what people felt in say 1970s or 1980s, that why to use silicon, why not other materials. So if you remember in the first lecture I told you there are different material and different generation of solar cell, and the generation comes from here. So silicon was the first generation, and it gave very satisfactory result. It has started from very basic to the very applied field. You just start with the understanding of the silicon material, and then you end up with solar cell panel and solar cell power generators. This is amazing. There is no doubt about it. But these disadvantages led scientists and researchers to think that let us change this material, or let us look for some alternate materials. So what are the alternate materials that you can think about? The materials which have relatively higher absorption. Okay, so and also little cost effective material. So why cost effective? Because silicon wafers are thick, so reduce the thickness of the wafer. That is the first challenge. Okay, absorption is one challenge, but people have started with thinking reduction of material cost. If I can make a 100 micrometer to 1 micrometer, then I reduce the material cost drastically. But people still thought that let us use silicon, let us not use other compound. So they have started thinking about it, and they came out with an idea of amorphous silicon. And particularly I can say that from 1970s to 1990s, there was a revolution in this amorphous silicon solar cell. Why? Because you can make it in a very thin film form, amorphous silicon solar cell. So whatever silicon I told you, these are crystalline silicon, but the amorphous silicon is another, allotrope of silicon, you can say, but they're in amorphous nature. So let me just show you very clearly. You already know what is the difference between a crystalline material and an amorphous material. You can see the two figures. So this is a crystalline material where all the atoms are sitting at a particular position and in a very ordered, well ordered manner. This is called crystalline structure. What is amorphous structure? Amorphous structure is that you do not have a large scale, ordering. If one atom is sitting here, another atom is here, and although they have small scale ordering, at very small scale they have ordering, but at large scale they do not have ordering. Okay, this is amorphous phase of the material. So people have introduced amorphous silicon, and there are some thin film technique by which one can also make amorphous silicon. I will come to those technique later in my other lectures. I just as a matter of introduction, I am introducing this thin film amorphous silicon here. So you can see this amorphous silicon is this structure and crystalline silicon is this structure. But the problem with amorphous silicon is that there are multiple or huge number of dangling bonds. You may be aware about dangling bonds. Dangling bonds are the atomic bonds which are not saturated. Okay. In case of the crystalline silicon, all bonds are saturated. One is connected with another and one is connected with another. So you do not have a free hand or free bond here and they are lying. But when you make an amorphous silicon, there are several free bonds which do not find atom. Okay, they are called dangling bonds. And dangling bonds are very nasty in that sense that dangling bonds actually create lot of recombination center. And therefore I mentioned that it is not good as solar cell. Because you have a lot of recombination center and huge number of recombination center, and the amorphous silicon cannot be directly used as a solar cell, although you reduce the thickness, but you cannot use a solar cell. So people are thinking to what to do in this. So what was done, that they have saturated these bonds by adding hydrogen in this. So making a structure amorphous, hydrogenated amorphous silicon. So what is the process of hydrogenation? It is very simple. You can see that you can have a very simple chamber. You can have it in your lab also. Okay. And in this, you put some gas called silane gas. Which actually, it contains silicon and hydrogen both. And then you add an RF power here, radio frequency power. You connect with this chamber. Okay, this chamber has two electrodes. One electrode is cathode, another electrode is anode. Okay, this is anode and this is cathode. And in between cathode and anode, when these silane gases come, then with the help of radio frequency power, you can generate plasma of this gas. Plasma means you can make it ionized state, silicon ion, hydrogen ion, all these ions can be produced in this plasma state or ionized state. And then this hydrogen gets incorporated in the amorphous silicon, because hydrogen is very light, it can very easily diffuse through the structure, and then you can see lot of dangling bonds. They get terminated by hydrogen. So you reduce lot of dangling bonds, you reduce the recombination center, okay, and you make a hydrogenated amorphous silicon, and then you make a solar cell out of this, and then compare with the crystalline silicon solar cell, which is a standard technology. So this is crystalline silicon solar cell, this is amorphous silicon solar cell. So if you look at the property, first you look at the band gap. So crystalline silicon solar cell band gap is 1.1 electron volt, and therefore it is a smaller band gap. Okay, and then your the lot of light cannot be absorbed. It goes to a large wavelength region to absorb this light, whereas your amorphous silicon is larger band gap, so you can cover more light in the visible part and also going to the UV part of the spectrum. So this is the importance. So this is the typical spectral range which you can absorb in case of crystalline silicon, and this is a typical spectral range which can be absorbed in case of amorphous silicon. However, the efficiency for crystalline silicon is much higher as reported so far, whereas amorphous silicon efficiency is much lower. This is a disadvantage of amorphous silicon. Okay, and therefore amorphous silicon was never used for large scale purpose. However, advantage is that amorphous silicon you have much lower thickness, 1 to 2 micrometer, whereas crystalline silicon the thickness is much higher. For absorbing same amount of light, you need 1 to 2 micrometer amorphous silicon or hydrogenated amorphous silicon, which is almost 100 times higher in case of crystalline silicon. So this is the disadvantage of crystalline silicon solar cell, although it is having high efficiency. Okay, there are some area requirement also. This is not a very important issue, but people have used amorphous silicon where they have used in the small devices like calculator or wristwatches, etc. So they are called micro power application. So in micro power application, people have used amorphous silicon, and as you know, it's a very thin silicon. It is 1 to 2 micrometers, so that it can be grown or deposited on a flexible substrate. Whether crystalline silicon, you cannot make it on flexible substrate. So it is flexible, and therefore there are wherever there is an utility of flexible solar cell, one can use amorphous silicon solar cell. It can also be used in high temperature environment because it is less sensitive to temperature as compared to crystalline silicon solar cell, and it is also environment friendly for PV application. Why it is environment friendly? Because it does not require those large number of production lines which or high temperature processing, where we have seen that the large equipments are required, and every time you had lot of gas emission for crystalline silicon production. However, the disadvantage is that its efficiency is less. Its efficiency is maximum efficiency is reported is 14%, whereas crystalline silicon efficiency is much higher. Okay, so it cannot be used for a purpose like if you want to make a power generating station or something, you want to put it in your roof to generate power for large production of power. This cannot be used. Okay, so I will come back to the thin film solar cell again with other material. Amorphous silicon is definitely one material which has initiated the research and technology in thin film solar cell. But I will come back to other thin film solar cell in my third lecture. But before that, let me introduce again light trapping process. Okay, so just recollect it. I was discussing light trapping in crystalline silicon solar cell, which is a thick silicon wafer. So how we did it, how we did this light trapping, we make a texturing or pyramid kind of structure on the surface, or we made a texturing in the bottom surface, and this is the way one can trap light. This is what I have already discussed. But when you make a thin film, okay, suppose you make a amorphous silicon solar cell or any other thin film solar cell, that chemical etching process is you cannot make a texturing. This is very difficult because that will almost eat up entire material. They are very thin. So we have to introduce some other processes to capture light. Okay, when we consider thin film solar cell, suppose we consider thin film amorphous silicon solar cell. So how to capture light in thin film solar cell? Okay, so one way to capture light by introducing what is known as plasmonics, or this is also known as plasmonic light capturing in solar cell. So what is plasmonic light capturing? Plasmonic light capturing is a process by which you whenever you shine light on a solar cell or any material, you create an environment by adding something on the solar cell so that you can capture more and more light. You do not make any texturing, no, you don't make any change on the surface, but you introduce something. So what I can introduce? I can introduce small metal nanoparticle. Okay, I take a surface and introduce. So this is solar cell, this is surface. So this is a solar cell, thin film solar cell. Okay, say typically 1 micrometer thick. And then I use some metal nanoparticle. And now light comes. Okay, these are metal nanoparticles. And light falls on this. Light fall. on this metal nanoparticle. So why I introduce metal nanoparticle? I do not make texturing because texturing, as I told you, is difficult for thin film. But how this metal nanoparticle on the solar cell, it will effectively increase the light trapping. Let me go to little fundamental, and then I will come back to a demo where you will be very clearly seeing that how this metal nanoparticle can be used for light trapping. So you can see that what is actually the plasmonic. If you look at very basic metal, you take a metallic slab here. Okay, so metals, you have many metals here and there. You use a lot of metals every day, but they are not charged. Okay, although if you look at the inside of a metal, take a cross-sectional view, it is basically large number of free electrons in the metal. Large number of free electrons in the metals. Okay, and then you have the positive ions beneath. Okay, so this is a typical inside view of a metal where you have large number of free electron and positive charge, but they are charge neutral because electron and positive charge numbers are same. So therefore, a metal as a whole is not charged. But by any means, if you make a movement on the electron, so it is electron gas, below is positive charge, and you make a movement in the electrons. So if you make a movement in the electrons, what will happen? Suppose these are electrons which are negatively charged. Below there is metal which is positively charged. You displace electron little bit, take it out with a displacement of U. So U is the displacement of electron. So therefore, as the electron is displaced now, these charges, positive charges which are there, they will try to attract by Coulombic attraction. Okay, so they will create a restoring force on the electron, and this restoring force will create a field which is 4 pi n e u. N is the electron density. So it will basically create two charges layer. One is minus NEU, there is one charge layer, and below there is plus NEU. When you have two charges layer separated by certain distance, then you have an electric field. Okay, so this electric field is 4 pi n e u. So this electric field will now try to bring the electrons back, and it will create a restoring force, and then this electron will start oscillating. It is exactly like your simple harmonic oscillator, like a pendulum, electron will oscillate. This is called plasma oscillation. Okay. So it is exactly like a sinusoidal oscillation of electron. Like a simple pendulum. And then if I have a sinusoidal oscillation of electron, I can also, if there is a sinusoidal oscillation, you all know that there is a process in quantum mechanics called quantization. If you quantize it, is a basic study, you make plasmon. So each quanta of this plasmonic oscillation of electron, you generate one plasmon. Okay, and how one can detect? It's very simple. You can just generate plasmon. You shine light on a very thin metal foil. Okay, or you just send very fast energy electron in a metal foil. Okay, by this method, and then this electron, when they passes through, they actually excite the plasmon, and so this is for typical plasmon spectrum from aluminum metal. Okay, so what you see this electron when it is passing through a thin metal foil, it is losing energy, generating two types of plasmon. One is bulk plasmon, another is surface plasmon. Okay, this is the quantization of plasma oscillation. Okay, this is the very basic you might have studied in the solid state physics, and this is the typical sinusoidal oscillation. You can see this is a typical sinusoidal oscillation, whenever you have a metallic nanoparticle here, as I told you, so each metallic nanoparticle actually acts like a something called localized surface plasmon resonance. Why the resonance come? Because when light falls on it, the plasmons are, they are vibrating in a particular frequency, as I mentioned, and then when light falls to its same frequency, there is a resonance. So there is a huge enhancement of electric field surrounding each, small metal nanoparticle. So that is the reason I mentioned that when you use a thin film, you do not do any texturing, put some metallic nanoparticle, and then you can have a localized surface plasmon resonance to trap light, you know, in very efficient manner in that sense, because by whenever you have a localized plasmon resonance, then the more light gets absorbed inside the silicon uh, wafer or in the thin silicon solar cell. So let me just show you one or two equations which are being used. So whenever the light falls on a particular metal nanoparticle which are embedded in a dielectric matrix, so these are metal nanoparticle NPs, and this is a dielectric matrix. So this is a typical configuration of a thin film solar cell or a plasmonic solar cell. And light falls. So some light gets scattered, some light get absorbed. So if you look at this scattered and absorbed light, the alpha is basically the polarizability of the material that and the volume of the particle which decide the absorption of light. And these are two quantities, epsilon p and epsilon m. These are basically dielectric function of the particle and dielectric function of the metal. So therefore, what are the quantities that play a role? The quantity which play a role is alpha, epsilon p, epsilon m, and volume of the nanoparticle. So these are the four important physical quantities of the material, of the metal and the surrounding matrix, which decide how they will be, trapped in the light, or how the scattering and absorption efficiency differ. So I just look at two case studies, and just you will understand that how this plasmon frequency changes. So you can see a silver metal nanoparticle which are grown on typically on silicon, uh, silicon dioxide, which is again coated on silicon. There is one is 50 nanometer silicon dioxide, another is 5 nanometer silicon dioxide. And typically the particles here, the silver nanoparticles, their diameter is 40 to 50 nanometer. So they are coated on these two substrates, and you can see this peak, and you can also notice this peak. You can also notice this peak. What are these peaks? These peaks corresponding to Q scattering peak. Q scattering peak is how efficiently it has scattered light inside the solar cell. Okay, so you can see this has a lot of effect. When I have a bare quartz, I do not have any coating on top of it. It goes to almost around 500 nanometer wavelength range. And when I have 50 nanometer SiO2 on silicon, it has increased little bit in between 500 and 600. And when I have 5 nanometer SiO2 on silicon, although the skew scattering probability is reduced, but it has covered a broad wavelength range. So this is the way one can tune the scattering probability. This is one way. And the second case study shows even more interesting, where instead of making nanoparticle, you make nanorod. Okay, you make silver nanorod or gold nanorod. Okay, so whenever you have nanorod, you have a length, you have a diameter. So you take a ratio of length to diameter of nanorod, length to diameter, and you call it aspect ratio, and change the aspect ratio and look at the absorbance of light, and you will appreciate as you change the aspect ratio, you basically tune the surface plasmon resonance drastically. So you can see how it is being tuned. It is being tuned from somewhere 700 nanometer to 1200 or more than 1200 nanometer. So huge, the spectral range you cover just by changing the aspect ratio of the nanorod. Okay, this is the importance. All right. So how my plasmonic solar cell configuration would be? Finally, I have, one thin film solar cell. Top of it, I grow some metal nanoparticle, or I just embed some metal nanoparticle inside the solar cell. Okay, so I have a dielectric function for the metal. I have a dielectric function for the matrix where I am embedding or I am putting, and then according to this dielectric function and the volume of the particle, I have, or the aspect ratio of the particle, I have different, the peaks for localized surface plasmon resonance, and I cover the spectral range. So once I cover the spectral range, what I have done essentially, I have trapped more and more light in my solar cell. Okay, so I did not change the thickness of the solar cell. I did not make any texturing of the solar cell. That is what I did in the bulk silicon solar cell case. In thin film cell, only I introduced this plasmonic nanoparticle and trapped light very efficiently. Okay, I think let me just summarize what we have discussed today. So the first, what we have discussed is that in order to improve the absorption of light in a silicon solar cell, what you need to increase the thickness of the active layer. But increasing active layer is always not possible because there are a lot of cost and recombination involved in that, which eventually increases cost with less performance, and therefore it was been investigated by researchers that one can make a texturing on the surface, or one can also make a texturing on the back surface in order to trap more and more light. Okay, and then what we have discussed is that what is the silicon manufacturing technology. So starting from sand and up to a module, what are the pathways or the production lines one is to look at or the involved in the entire silicon solar cell production, and we have discussed about it, and we have also seen that all the production lines are there are a lot of involved technologies with high temperature processes, chemical processes, etc. are involved, and therefore it enhances the production cost. Moreover, with less absorption, with certain disadvantages. The introduction of thin film solar cell in the technology was done in few decades back, and what people have suggested that if we do not take the crystalline form of silicon, but if we take amorphous form of silicon, we can have a thin silicon solar cell which is amorphous silicon based, and we have discussed a little bit about the amorphous silicon solar cell. We'll discuss more about it when we discussed in detail about the thin film silicon, thin film solar cell, but we made a comparison of amorphous silicon and crystalline silicon solar cell. And finally, what we have discussed is the plasmonic light trapping process, that when we consider the thin film solar cell, we don't go by the texturing process. We don't texture the surface. However, what we do, we introduce metallic nanoparticle on the solar cell. Either you put it on top of the solar cell or you embed the metallic nanoparticle, and this is a process of plasmonic light trapping. And with this plasmonic light trapping, one can have a better performance of the thin film solar cell. Thank you.